All right, let's just jump right into this explainer because we've got to unpack some absolutely brilliant engineering inside DeepSeek V2's architecture. If you've been tracking the breakneck speed of large language models lately, you already know that scaling up isn't just, throwing more compute at a model anymore. It's about fundamentally ripping up the floorboards and rethinking how the architecture handles data. So today, we're exploring a massive breakthrough. It's called Multi-Head Latent Attention, or MHLA. And honestly, it's a total masterclass in efficiency that literally rewrites the rules for how attention mechanisms operate under the hood.
But to really get why MLA is such a game changer, we have to start with a serious problem that plagues basically every major language model out there: memory limits. When a model generates super long text, what is actually causing your system to run out of memory and crash? Now, you might be thinking it's the heavy matrix math for generating tokens, but actually, scratch that. Matrix math isn't what's filling up your VRAM during generation. The real culprit is something else entirely. It's this silent accumulator just quietly hoarding space in the background of the attention mechanism.
And that brings us to the core issue, the KV cache. Think of the KV cache as, well, a massive memory thief. To avoid recalculating past context, the attention mechanism stores a key and a value for every single token it processes. But here's the kicker. It doesn't just do this once per token. It does it for every single attention head in the network. So, as the model generates longer and longer text, this memory store just grows and grows without bound. It keeps hoarding resources until it hits a hard physical limit and just stops your generation dead in its tracks. So, our roadmap today covers exactly how they solve this. 1. The memory wall. 2. Cache fees diversity. 3. Compress, do not share. 4. The absorption-free lunch. And finally, 5. The rope wrinkle.
All right, kicking things off with Section 1, the memory wall, the hard physical limitation of AI.
To truly appreciate the sheer scale of this problem, just think about the number 1. For every single token generated, attention has to store one key and one value for every single head. So if you're using standard multi-head attention, and say you have 32 heads, you are storing 32 distinct keys and 32 distinct values just for one single word. Now multiply that by thousands of tokens in a document, and then multiply that by the dozens of layers in a modern transformer. It creates this absolute, unbounded mountain of cached data that simply won't fit into standard GPU memory.
Which leads us to Section 2, cache versus diversity, and the flawed compromises of the past.
For the longest time, engineers have been stuck in this frustrating tug-of-war. On one side, you've got traditional multi-head attention. It gives you incredible diversity because every head learns to look at the text in a completely different way, making the model super smart. But as we just saw, it creates that huge unmanageable cache. On the flip side, the classic fixes were multi-query and grouped query attention. Now, these shrink the cache dramatically by forcing all those different heads to share the same keys and values. Sounds great, right? Well, here's the fatal flaw. The moment those heads read the same key, they all look at the token in the exact same way. You buy a smaller cache, for sure, but you completely erase the head diversity that made the model capable of complex reasoning in the first place. You are effectively lobotomizing the attention mechanism just to save memory.
So how do we fix this? Enter Section 3. Compress, do not share. This is the core innovation of DeepSeek V2.
To completely break this trade-off, DeepSeek V2 introduces multi-head latent attention, and it's built on one very specific philosophy: compress, don't share. Instead of taking the easy way out and forcing diverse heads to share a single representation, the engineers asked a radically different question. What if we just compress the data we need to store? That way, the cache itself becomes incredibly tiny. But, and this is absolutely crucial, the distinct perspectives of the attention heads remain completely intact.
And here is the actual mechanic behind how they pull that off. It's basically a 3-step process. First, a down projection squeezes the massive hidden state into one highly compressed, small latent vector. Second, that single tiny vector is the only thing that gets saved to the KV cache. At this point, the cache is totally head agnostic. It has no clue about the different attention heads. But then we hit step 3. When the model needs to generate a token, it uses per head up projections to rebuild the full, distinct keys and values right on demand. So it's like you store a tiny zipped file, and then you unzip it into unique perspectives for every single head exactly when you need them. The cache stays impossibly small, and the heads stay wonderfully diverse.
But wait, there's more. Let's look at Section 4, the absorption-free lunch, optimizing the reconstruction.
Now, if you know anything about neural networks, rebuilding unique keys on demand for every single token probably sounds like an absolute computational nightmare, right? Well, enter the magic trick, the free lunch of absorption.
In machine learning, a true free lunch is incredibly rare, but MLA actually delivers one here. Because neural networks run on linear algebra, you don't actually have to do the heavy lifting of up-projecting and rebuilding those keys in a separate isolated step. Thanks to the associative property of matrix multiplication, the math basically allows these up projections to just fold straight into the query and output matrices.
Think about what that actually means for a second. Because those projection steps are absorbed right into the existing weights of the model, the attention mechanism runs directly in the compressed latent space. There is literally no massive computational spike for reconstruction at all. Looking at it from the outside, the memory footprint and the compute speed look exactly as efficient as that lobotomized multi-query attention we talked about. But under the hood, mathematically speaking, it acts like it has full multi-head diversity. It's wild. You get the memory savings of sharing, the intelligence of diversity, and the speed of skipping the reconstruction step entirely.
Okay, bringing us to our final part, Section 5, the rope wrinkle, the real-world engineering hurdle.
Of course, in the real world, theoretical math always hits a practical hurdle. And here, the hurdle is rope, rotary positional embeddings. Almost all modern models use rope to help understand the order of words. The problem? Rope applies a position-dependent rotation to the keys, and that rotation completely breaks the beautiful matrix math that gives us that absorption-free lunch. I mean, you can't just absorb a matrix if it's constantly rotating based on where it sits in a sentence. So, the engineers came up with a highly elegant fix. They simply split the key into two lanes. They made a large lane dedicated purely to the content of the token. Since this lane has no positional rotation, it can be fully compressed and completely absorbed. Then, they carved out a tiny, shared lane strictly for the positional rotation. By separating the content from the position like this, they preserve that mathematical free lunch while still letting the model understand word order perfectly. So what does this all mean for us? Well, the crucial takeaway here is that multi-head latent attention has successfully bypassed the memory wall, and it did it without sacrificing an ounce of the model's cognitive diversity. It really is an engineering marvel that gives us the best of all worlds. By solving the memory crisis through latent space compression rather than just lazy sharing, we really have to wonder, will this elegant trick completely define the architecture of the next generation of AI? As context windows keep stretching to millions and millions of tokens, it is very possible that compress, don't share won't just be DeepSeek's personal philosophy, but the absolute, unquestionable standard for every single model to come. Definitely something to think about.